So the main idea of this workshop is to start a high-level discussion, scientific discussions about the possibilities of research here in UFRJ, together with our group in cooperation with heriot-watt. So the starting point is what they are doing in heriot-watt and new techniques for EOR that will be presented, and then we'll present what we are doing here. Thank you.
Thanks very much for the opportunity to be here this morning and present to you some of the highlights of what we do at heriot-watt around enhanced oil recovery. We are extremely excited about the prospects of collaborating with UFRJ, and as Paolo said, we've been discussing this project for some time now, and there has been a lot of work going on in the background, and yesterday we had also some more work to bring this one step closer. But let me be very upfront here. This is a major project. It's not something that any one of us could underestimate. There is a lot of things that we need to put in place, and a lot of things that we need to start here, and everybody involved in the project will know that, be on a very steep learning curve to do that together. But it is doable. We come from heriot-watt University. I have my colleague here, Sean Ireland, with me. Heriot-watt is in Edinburgh. If you're lucky to avoid rain there, Edinburgh is a beautiful city. This is a picture of Edinburgh. I've been there for 17 years, and I loved every minute of that. It's a very good and beautiful city to live there. Heriot-watt, in case you're wondering what's Heriot, what's that dash in between. Heriot was a money financier. The name of the person that donated the land that the existing campus of heriot-watt moved 2 years ago from the city center to the existing facility. Those of you who've been there, and I'm sure Paolo would agree with me, that the campus is a beautiful campus. It's a mixture of a modern building campus as well as very mature trees, etc. It's beautiful. I'll say this to encourage you to apply for the positions that Paolo just said. You will not regret it. It would be an excellent experience. You have Juliana's name. Feel free to contact her to see how her experience has been and so forth. So Heriot is the name of the guy who donated the land, and Watt is the famous James Watt guy, steam engine, etc. But as always, money goes first. So the name turned out to be heriot-watt rather. So it's the name of two persons. But we're really glad, because if it was Watt Heriot, then it would have been a bit of a nonsense name there. So that's the name. Our main campus is in Edinburgh. Edinburgh is the capital of Scotland, and Scotland may become independent in September this year. If you are interested to know more about that, I have a red-blooded Scots with me. You can feel free to talk to him later on after the meeting. We have another campus in Dubai, a relatively modern campus there, despite being there only for a few years, but it's been ranked as one of the very highly regarded universities in Dubai. You may not know, but many top universities, American universities, have a branch in Dubai. So it's quite competitive to have a presence there. We also have recently started a campus in Malaysia. Again, heriot-watt University was selected out of a number of high-ranking universities around the world to set up this campus funded by the Malaysian government. So Institute of Petroleum Engineering, the same way that you have a system of ranking here in the UK, there is a system of ranking university based on the research that they do. We call this RAE, Research Assessment Exercise. It's an exercise that is done every 6 years. And all universities in the UK will be assessed by an independent panel based on their research output, and they are ranked. heriot-watt for 10 years in a row has achieved the highest ranking, which is the 5-star ranking that you could get. Each department is different. So that's the ranking of the petroleum department, not necessarily the whole university. There's only one other department with that ranking, and that's where David was graduate, our competitor, Imperial College, in the whole UK. So it's a highly regarded Department of Petroleum Engineering, and it's really a success story that listening to the ambitious plans that you have for here, I hope that heriot-watt's story would inspire you. Started 40 years ago when the offshore oil and gas started in the UK, which was really at the time the biggest challenge that the oil and gas industry was facing, much bigger than the challenge of developing pre-salt here in Brazil. The department was formed to essentially address those challenges of operating offshore, setting up platform drilling, producing from these reservoirs miles away from dry land in the middle of in the sea was a great challenge. And nowadays, the UK position is probably the best among offshore industry, and the expertise developed over the past 40 years in Aberdeen, and a lot of it due to the work done at heriot-watt Petroleum Engineering Department has now been exported all over the world in major oil and gas hubs. Started 40 years ago in a small city, Edinburgh, no oil at all. The only thing that was special about Edinburgh was that it was 2.5 hours away from Aberdeen, which was to become the center of this offshore oil and gas production. But it's famous for its applied research. You may have heard of JIP, Joint Industry Project. The term was actually coined at heriot-watt 40 years ago, a business model for running research. It's expensive business, but in JIP model, a number of companies, each one would pay a ticket price to set up a research designed to address a problem, to solve a problem for the industry or to improve an existing methodology. 90% of our research comes from industry, so very much applied type of research. We don't have any undergrad student. All our students are postgrad. Our flagship master course is our PE course. Many experts and managers throughout the world in the oil and gas industry have actually gone through our PE program. Highly regarded petroleum engineering master course is a 1-year course. And PhD and MPhil student. You may be surprised to hear that our master course in PE is actually the largest in the world. We are a tiny department. We know that. We are not huge. We don't have very many staff. But I honestly believe that we are probably one of the most efficient departments that exists in the world. We are able to run the biggest PE program in the world. Now, if you put that in the context of all the universities that you have offering PE, some major ones in the US, it's quite an achievement for a department in a country which is around 5 million people. That's less than what you have in Rio. That's the sort of success story that I hope you take as an inspiration, really, for UFRJ. You can become a center like that in Brazil. Brazil itself is on its way to become a major hub here for oil and gas, not just for Brazil, for the whole world. We have around 110 researchers and support staff, 10 research groups, covering most of topics around subsurface, not just EOR, production, geology, scale. There are a lot of things. So we have groups addressing all those issues. The group that I am involved with is the enhanced oil recovery. So why enhanced oil recovery? Here are some production curves, monthly production curves from 4 fields in the UK basin. This is production rate, and this is essentially time. And you could see that all of them are showing a very steep decline. Unfortunately, it's very familiar stories for many reservoirs in the North Sea, not just the UK. On the Norwegian sector, the decline is even faster than this. And the Norwegian government is really after technologies that can either reverse this, which would probably be a very difficult thing to do, but at least to try to reduce some of the slope of this declining rates. This is a major issue. You have many people in that area working in this industry. It would have a major impact on the cost of energy and everything. So you could see that there is really a problem there that has to be addressed. And while oil production's dropping so rapidly, this guy is rising so rapidly. So this is oil price and time. You could see that it has been rising and has been over $100 per barrel, significantly over that mark for a long time now, to an extent that oil and gas companies are now placing our policies and strategies based on that sort of prices. David would confirm that normally oil companies have a price that would be less than the existing price of oil, and they plan based on that price, because historically oil price can go up as well as going down. If you have some excess production, oil prices could drop. But the demand has been so high, and the projection for future demand is so high, that we don't think that anytime soon oil prices would drop significantly below 100. And this is representing a significant opportunity as well as the challenge. Here is some data from IEA. The blue curve here shows the projection for the demand for energy is going up, as you could see, and the red curve shows the oil production. So currently, to run the world as it is, every day we need to produce around 90 million barrels of oil. But you could see that the projection is that there will be a very sharp decline. This sharp decline is due to those decline curves that you notice from those reservoirs. Now, of course, in the mature basins like the North Sea, you have a decline, but there are in some other parts of the world some new reservoirs being found, like the pre-salt here. But generally speaking, there is a gap that is being developed between how much oil we need and how much oil we are producing. And somehow this gap should be filled. And there is essentially 2 ways that you could fill that gap: either find new reservoirs and bring them on production, or take more out of the existing reservoirs. In here you see the exploration rate, the success rate. Lots of giant fields were found many years ago, in 1970s, and we have been producing from these giant reservoirs. But if you look at the current success rate, it's been much, much less now. Going forward, we don't expect to see very many large reservoirs for a very simple reason. In the business of exploration, the large reservoirs are found first. So most of these huge reservoirs have already been found. There will be a few, like the pre-salt here, that because of the advancement in technology, you'll be able to produce. We probably knew they were there, but it was challenging before to produce from them. Or like unconventional reservoirs, shale oil reservoir, very heavy viscous oil reservoirs. They, with time, as the technology progresses, it would become possible to produce from them. But those will be much more expensive to produce, because this was the conventional or easy oil, most of which have been found. So then we are left with 2 main techniques, essentially to try to improve recovery from the existing reservoir. There's a saying that goes, the best place to find oil is in an oil reservoir. So go back to your oil reservoir and see if you can increase its recovery factor. The business of oil and gas production is unfortunately extremely inefficient. On the average, we are leaving behind in every reservoir 70% of the oil that we know it is there. In some reservoirs, more complicated viscous oil reservoir, that number could be only as high as 10%, meaning that you produce only 10% of the oil, leaving behind 90% oil still in the ground. And I was thinking this morning, I think it was around 28 years ago, when I was sitting on the other side of the desk, and I realized that, you know, we're leaving so much oil in the ground. And I was fascinated by, you know, prospects of, I surely be able to develop something to increase this number to much higher. And I spent my career on that. Good luck with you. I hope you can come up with something to increase that number. It's extremely difficult and challenging to do that. But it's now becoming a must for us to try to increase recovery factor. Essentially, the industry does two things. Either we do more drilling, we call this infill drilling. This is drilling more wells in between your existing wells. And if you drill more wells, especially in those areas that have not been already produced for whatever reason, then you can get more oil out. We call that infill drilling. Or do EOR. EOR is any technique that goes beyond water flooding. Most reservoirs at some point in their lives are under water flooding. In the North Sea, water flooding is the standard recovery method. Every reservoir is all under water flooding. These are good quality sandstone reservoirs. Plenty of water is available offshore. It makes sense to filter water and pump it in the reservoir. In fact, we call ourselves oil industry, but we should call ourselves water industry, because we inject more water and we produce more water that we produce oil. In many wells, in mature reservoirs, water cut or fraction is around 90%, meaning from every 100 barrel of fluid that you produce, 90 barrel of that is water, only 10 barrel of that is oil. So there is a lot of water is being injected and is being produced. Anything that you do after that water flooding is under enhanced oil recovery. These are usually sophisticated method, including application of chemicals, gas injection, steam, etc., etc. So out of that 90 million barrel per day that I say we produce every day, how much do you think comes from EOR? Any idea? Out of 90 million barrel that we produce every day, today, how much of that comes from enhanced oil recovery? Half? 2 million? Only 250,000 barrels. Only 250,000 barrels out of 90 million barrels. It's nothing. Right? And most of that 250,000 barrels of EOR comes from thermal EORs applied to viscous oil reservoirs. Those are reservoirs that you start by EOR because the oil is so heavy that you won't be able to flow it. So mostly you steam inject steam or something thermal, because luckily the viscosity of crude oil responds very well to heat. So you could heat it up, viscosity drops, and then you could flow it. So it's really nothing. So the question is, why? Why? We know we need more oil. Oil price is high. There are techniques that people have been developing for many, many years. Alkaline surfactant chemical flooding is more than 70 years old. Why we are not applying these? It's costly. It's difficult to plan, and this is the challenge. So there are lots of opportunities, high oil prices, high demand for energy, but there are big challenges too. And the challenge is uncertainties associated with estimating how much incremental oil recovery or additional oil recovery you may be able to obtain if you injected this chemical, if you injected that gas, if you flooded with CO2, etc. How much additional oil you would get. This is the average recovery factor from the North Sea, the UK continental shelf. You could see that average recovery factor is around less than 50%, 40-something%, meaning that the tank is still half full. So, and these reservoirs are amongst some of the best reservoirs in the world. The global water flood recovery factor is only around 30%, average globally. In the North Sea, there are reservoirs like Piper that produce with 70% recovery factor, extremely high recovery factor for an oil reservoir. Nevertheless, the total recovery factor is only around half and less than that, meaning that half of the oil is still in place. And the question is why we don't do more EOR. And I say these things because you're starting now, and there's plenty of opportunity for you to get involved. Certainly, in my career, over the past 30 years, I don't remember of any time more exciting than the time that we are going through now. There is lots of opportunity for people to get involved. EOR day is today. 30 years ago was too early. There were plenty of light oil to produce. The cost of producing a barrel of oil in Saudi Arabia is less than $10 per barrel. So why people would do an EOR if you could go into a huge fracture reservoir by only 10 centimeters and get 100,000 barrels per day oil production? Why would you bother with doing an EOR? It was too early. 30 years down the line, it's probably too late. Somebody's come up with something. The day of EOR is today, and the day for you to get involved in these things. And you should not think, well, if people could not do anything in the past 70 years, why would I be able? Because things have changed now. We have technologies that we didn't have before. And what we want to do in UFRJ is essentially to set up just a platform, nothing more than that. Just a platform for people like yourself with lots of talent to get involved and come up with ideas that are fit for purpose today and can produce from this. But going back to that question, why out of 90 million, only 250,000 coming from EOR? Is because this industry is special. It's very special. It's a very lucrative industry. There are a lot of money to be made in this industry. But why we don't have hundreds of companies all rushing to become oil company to produce oil? It's a very upfront, large investment and risky business. To give you an example, very few oil companies are bigger and more powerful than BP in the UK. One of the largest, a giant oil reservoir. It came this close to bankruptcy a couple of years ago. It's still been limping after that incident in the Gulf of Mexico. That one well blew up and caused that disaster. Is it 3 years now? 4 years maybe? 4 years now. It's been limping. This giant oil reservoir has been limping since then. How many wells do you think BP drills? Probably thousands of wells. How many went wrong? One. Right? So it shows you how risky this industry is. It doesn't take much to go from being very successful, making a lot of money, to becoming bankrupt. The difference is a very thin line. So you cannot just make decision based on not completely analyzing things, reducing uncertainties. 2 weeks ago, I was somewhere, and I was contacted about a giant reservoir that is now in big trouble. They have injected nitrogen in a gas condensate reservoir. Gas condensate reservoir are a very important class of reservoir. The reason for that is that they can produce a cut of petroleum which is naturally refined, condensate. is the premium fuel. It's the most expensive part of the oil, petroleum that you can get. Back in the World War II, the country that I come originally from, Iran, was invaded by big boys running the war. And there was not enough refinery for all the planes to fly. And condensates were produced directly from the well, put in a plane, and flying plane directly. It's so naturally refined that you could use it directly without any further refinement. In such reservoir, I don't mention the name of a company, but somebody's injected nitrogen, right? Nitrogen injection is not something easy to do. Where do you get your nitrogen from? You need to have a nitrogen plant. What size do you think this plant would be? Like the size of a city. You need to have to separate nitrogen from air. It's a huge undertaking. Years of planning, etc., etc. It takes some time before you could see the consequence of your action, right? How many years? 3 years. What happened after 3 years? The condensate cut of this oil, which is the actual thing that you're after. The gas itself doesn't have much value. In fact, we re-inject the gas back in the reservoir to do pressure maintenance. So we produce this to get that liquid part of it, which we call it condensate. 3 years down the line, this condensate dropped from initial 12% to only 5%, right? And it's not going back up. So instantly, you spend so many years injecting this, so much money to design this, and instantly you reduce your revenue significantly. And it's not going to be fixed, this problem, for years to come. So there are consequences, huge consequences. It is not that you inject something in a reservoir and necessarily you see a positive response. It's not that you inject this chemical, etc., and necessarily you get something. You can do things to your reservoir that would permanently, irreversibly damage your reservoir. So these things need planning, need technology. Most of the models that we use today, they are not very accurate. You need to have good labs, be able to do good experiment, and then be able to apply that correctly to your field to see the benefit of that. So this is what we've been doing in our group at heriot-watt for the past probably 3 decades. I've been involved for the past 17 years in the group. Essentially what we do is 2 things. Improving our current understanding of recovery processes to avoid things like that example of nitrogen injection, etc. And the other one is to generate data that companies require to fine-tune their models to then be able to predict performance of a reservoir. I think we have a unique research approach, and this unique research approach is the basis of what we are trying to do here. We look at recovery processes at the smaller scale, at micro scale, in what we call the micro model. Remember that a reservoir could be the size of a city, but everything starts from these tiny pores that you can't even see them. If you look at a reservoir rock, which looks like a sandstone, normal sandstone used in construction, you won't be able to see those pores, but everything starts from those pores. So it's important to know what happened at that dimension, at that scale, what happens in there. That's where we look at things first. But the advantage that we have, and we've been pioneering this technique for the past 30 years, is that we can look into what happens in these pores under the actual reservoir pressure and temperature, using the actual reservoir fluid that you have, crude oil, gas condensate, whatever that system is, exact composition of that oil and pressure and temperature. It's like a window that you can open in the middle of your reservoir rock and see what happens when you inject water, when you inject this gas, that chemical, etc., etc. It teaches you a lot of physics. And I think one of the reasons why we've been able to be maybe one step ahead of other groups working similar sort of thing is the knowledge that we gain over years by doing these type of experiments. We then look into things at a larger scale, core scale. From every well that we drill, we take some cores, and then inside these cores, we essentially physically simulate those processes that happen in the reservoir. And then we look at what those mechanisms that we've seen at pore scale, which one of them are important at that scale? That is another thing that we do. Plus, we quantify these. In the oil and gas, we use numerical simulator to simulate numerically a reservoir. Those simulators require data. The data is generated, most of the data is generated from these core flood experiments. So that's what we do. And then we use the result of pore scale and core scale, and we develop our own mechanistic model or numerical simulator for applying this knowledge to the field scale. That is the ultimate scale that we need. We have very good facilities. Most of the laboratory facility that we have been designed at heriot-watt and have actually been manufactured there. Here is one picture of some of these labs. Plenty of students. There is something about EOR that when you get involved, you lose your hair. So it's me, it's Sean, it's Heron. And we are not relatives. We are from different parts of the world. So it must be that. So Heron's from Mexico. He works on Pemex reservoir, some really challenging reservoir Mexico has. These are carbonate reservoir, maybe similar to what you have here in Pre-Salt. Vuggy, fractured, huge reservoirs. But the oil is very high viscosity. Temperature is much higher than typical temperature of reservoirs that you have here. Some of the lab pictures, a relatively new rig. As I said, we design and we build these equipment here. The hardware is designed to really be able to work with any type of fluid. And we are talking about very high salinity brine, which is extremely corrosive. Low pH fluid, like when you have CO2, stuff like that. Most of the components that we use in here are made of hastelloy or alloys like titanium. They're really resistant to any type of fluid that you can use at such high pressure and temperature that your reservoirs are. Some picture, not very pretty picture, but I'm afraid that's how the workshops look like, especially an active working workshop. We machine and design these things ourselves. And there is a big difference between what we design and manufacture compared to what you can probably buy off the shelf. We are the end users. We are the guys that we know the expertise around pressure, high temperature. We design what we need to do, that piece of work that we need to do. Whereas companies producing laboratory, they don't necessarily know how this piece of equipment is used or what's the best way of running that. So that's what we have, sort of introduction around what we have in there. We have some projects. As I said, most of the model that we use is this joint industry project, a very cost-effective business model because each company pays a ticket price typically between 30 to 50,000 pounds per year, and then they get a research value equivalent to maybe 10 times that if you have 10 partners in that project. So very cost effective. We do a lot of work around this water alternating or WAG injection. It's a very important technique for oil recovery and suitable for oil reservoirs that you have here in Brazil. There's a lot of interest around application of WAG in reservoirs here. We use CO2 foam injection for improving recovery mainly from viscous oil reservoirs when water flood itself or CO2 also is not that effective because of the large contrast between the viscosity. Foaming with CO2 could be a solution for that reservoir. This has been very successful to an extent that there is at the moment a major pilot test being done based on the result of this project. One of our partners is ConocoPhillips on that project. In the North Slope, Alaska, they are doing a pilot test based on the result of this project on CO2 foam injection. I know Paolo is also interested in that technique. We are looking at mixing water in CO2 in the water that we inject in every reservoir and essentially produce carbonated water, inject that in in oil reservoir for improving recovery. That is another technique. This low salinity water injection has recently attracted a lot of attention. If I want to say just one new technique, most of these EOR techniques are very old. At least the fundamental is old. Now you may have a new polymer, new chemical to use, but polymer injection or chemical injection is nothing new. If I want to just mention one new technique, is this low salinity water injection, reducing the salinity of the water that we inject. Typically, seawater has between 30,000 to 50,000 ppm of salt, depending on where that sample of seawater comes from. In low salinity, you're reducing the salt content to around 1,000 or 500 ppm, a significant reduction in salinity, and that has been shown that can improve the recovery of oil. BP, one of our partners in that project, is running a pilot test in the North Sea in Clare Reservoir. We do CO2 injection in carbonate reservoir. This one is specifically on carbonate rocks. We have a project around gas condensate injection. We have also a number of projects that are between us and individual companies. They are not joint industry project. We have a commercial vehicle for our group, and that is because the companies working with us, they often wanted us to do things that were not really research. They were like service type of things, doing a measurement that normally they would go to a service company like Core Labs, things like this. But they wanted us to do that because they thought we were maybe a better place to do that. We are a knowledge-based group. We are not a commercial entity, so we can use the knowledge that we gain in our research and apply that to the service type of work that companies would require. So we set up in 2009 this company in Edinburgh to essentially provide that type of service. This photograph is now old because some of these guys are now left. John is now in Houston working for BP. Panta is working for Maersk. People have gone their own ways. And the number of students that we have, these are mainly PhD students. A cold winter, see the ice here on the grass in Edinburgh. A cold, crisp morning winter there. We get very good support from industry. At any time, between 20 to 25 companies are partner in the projects that we have. They don't necessarily support all the projects. They can pick and choose which project they want to support based on their interests. And companies, different companies have different priorities. An oil company may not have any viscous oil in their assets, so they won't be interested in heavy oil. Whereas they may have interest in, for instance, WAG injection or CO2 injection because they have CO2, for instance, available. So good support from the industry. Let me show you just one example. I'm not going to go through all the slides that I have because I think I probably will run out of time. But just to give you some of the examples of what we do. Here is the slide that I was attending a conference in Aberdeen in 2010. And DEC, this is the Department of Energy and Climate Change in the UK. It's similar to, equivalent to DOE in the States. Presented this based on the feedback getting from companies operating in the North Sea, asking them, what EOR technique do you think has the highest potential? This is the feedback from them. So the blue, as you could see, this is a huge chunk of this additional oil recovery, is by gas injection, including CO2. So lots of companies thought that CO2 and gas injection in general has the highest potential, followed by chemical injection, polymers, surfactant, etc. Heavy oil, there are a lot of reservoirs with viscous oil that companies not been producing because they had lighter, easier oil to produce, but now they're interested in producing that. So one of the GIPs that we have is looking at this gas injection and WAG injection, water alternating gas injection. I could see that there is a very significant interest around this technique. One good or advantage of gas injection is that normally mechanisms associated with gas injection are physical. And physical mechanisms are relatively easier to understand compared to chemical. If you have chemical reaction in a reservoir, sometimes it would be extremely difficult to fully understand how those chemical reactions happen. So in WAG injection, in a well bore, you inject gas and you inject water. Gas viscosity is very low compared to water and oil in a reservoir. So if you just flood a reservoir with bulk gas injection, then gas tend to override your oil, as you could see here, and then very quickly move to your production well and get produced. To not eliminate completely, but alleviate, reduce this problem, anytime that we do gas injection, we intermittently inject slugs of gas with water. So inject one slug of gas, chase that with water, another slug of gas, chase that with another slug of water. We call this water alternating gas or WAG injection. And then inside your reservoir, you produce an envelope, a region that you have three-phase flowing: oil, gas, and water. Depending on the properties of the reservoir, thickness, for instance, kV, vertical to horizontal permeability, at some point inside the reservoir, gravity wins, and gas again starts overriding oil, and water sinks down towards the lower part of your reservoir. In Prudhoe Bay, BP's been applying this technique for many years, and what they did in this part of the reservoir, when you have unswept oil, the black area here, they drilled horizontal well and injected WAG through horizontal well, targeting those areas. Okay, it's all good. It's been tested. There are review paper on this on more than 55 or something reservoirs under WAG injection. And often it has been a successful technique. The challenge is that because you're injecting gas and water in slugs, then the process is what we call it imbibition followed by drainage, followed by imbibition, followed by drainage. And then how you characterize these, and you probably know that the way that we simulate numerically our reservoir currently depends on applying curves that we call them relative permeability curves to our blocks of the reservoir. We essentially divide our reservoir into smaller blocks, and for each block we write the equation of flow, and for each phase that we have, oil, gas, water, we use one of these curves that essentially shows how fast these multi-phase system, how fast these fluids flow to get to the other part of the reservoir. That's what relative permeability is. Your numerical simulator is heavily dependent on these curves, right? But these curves are not actual physical properties. They're actually fudge factor. They don't exist. They don't have any physical meaning. A French hydrologist many years ago empirically developed a correlation when he was filtering water through sand filters, and he noticed that there was a relationship between flow rate and the head of water that you have in those sand filters. And then he came up with this empirical correlation called Darcy correlation. Darcy is only valid when you have steady state single phase flow. We use Darcy at the center of our simulator. So no matter how fancy your simulator looks like, no matter how good its graphics is, no matter how 3D, 4D, whatever you want to call it, all that, the engine is that Darcy equation. Now, because we didn't have any better equation, we modified this Darcy equation, which the poor guy said it's only valid for single phase fluid, but we don't have any single phase oil reservoirs. In any oil reservoir, you at least have two phase, oil and gas. Sometimes you have three, oil and water. Sometimes you have three, oil, gas, water. Sometimes you have more, right? So what we did, we modified, if you like, in inverted commas, the equation of Darcy, and we defined this relative permeability and say we apply it for multi-phase, and instead of using an absolute permeability, we use a relative permeability. So that's why I call this a fudge factor. Such thing doesn't exist, right? And then we measure these things to then put this in our simulator. This is an essential part of your simulator. Now, when you have gas, water, you have a hysteresis, because you have gas injection, you have one curve, then you have water injection, you have another curve. Then you switch to gas injection, which would be a different curve, not similar to the first gas injection, because you have what we call a cycle hysteresis. That gas injection was first cycle. Then you have another cycle, second cycle. You have third cycle. And each cycle, in general, could have a different relative permeability. How do you obtain those relative permeabilities? How do you define those changes between each cycle for gas, for water? These are sort of empirical that you do the measurement. So it's extremely difficult to obtain these. To obtain those curves, you need to perform experiment under actual reservoir condition, which would be extremely time-consuming to do. Right? Let me look at this. This is the data that BP's published. You could check that SPE paper there. Again, for the Prudhoe Bay reservoir, they simulated for a well that if you inject miscible gas, you could get two scenarios. And this is the amount of additional oil recovery. One is this thick line, and the other one is this thinner line. The two of them, the dashed line. So this was the prediction of simulator, right? If you did WAG in this well, you get this much oil recovery. One of them was based on having a thief zone, because in addition to multi-phase flow, you have uncertainties around your geology. What do you have down in the ground? Who knows? You just penetrate some wells in there, which in the grand size of a reservoir, it's like a needle in a haystack. It doesn't give you much information. So you have all that. But they did two scenarios, one with a thief zone, so that would be the prediction. One without thief zone, that would be the additional oil recovery. And then based on that, they went ahead and they did gas injection. No company, no oil company injects anything in any well before they've run some simulation, right? And before they are convinced that what they see is accurate enough to give them enough certainty that would convince the management to go ahead with this, right? So they did this, and based on this, they thought it was good enough. They went ahead and inject WAG in that reservoir. And then the response, the actual response, this is prediction of a simulator. The actual response was this. These are not inexperienced people, right? These are probably the best reservoir engineers that you could find. And that is the discrepancy between what happened and what was predicted, right? Now, whoever this reservoir engineer was extremely lucky, because if this was the other way around, his days in that company would be very limited, right? Because there will be a lot of costs associated with doing these. These are not games. Injecting gas in a reservoir is not a game. Installing compressor, the cost of these compressors, bringing gas, etc., huge investment, right? So you could see that there is massive discrepancies because of those curves. How do you define flow in those grid blocks? So these are extremely important. This is a subject that we've been working on for the past 17 years. I'm not going to go through detail. If you want to know more, apply to Paolo for a PhD. Come there, then we have a chat around it. But for today, it's enough. What we have done is just show you this part, and maybe I stop there. What we have done is there are some models in every reservoir simulator, like these. We call these three-phase relative permeability models. Very quickly, what you do is any company spends a lot of money on programs. We call them SCAL, Special Core Analysis. And they do relative permeability measurement, capillary pressure measurement, these sort of things. The standard procedure is that for a SCAL, you only look at two-phase scenarios. So you do gas oil, two-phase system, relative permeability measurement, and you do water oil, two-phase system, relative permeability measurement. And then, because three-phase would be extremely difficult to do. Having three-phase simultaneously flowing would be extremely difficult thing to do. As I said, these are maybe discussions for later. But what we do currently is that we perform two-phase SCAL measurement, and there are correlations in any reservoir simulator, irrespective of what you use, Eclipse, VIP, CMG, whatever. You have some correlation. Here's probably one of the well-known ones, Stone 1. Stone is the name of the guy who essentially proposed this model. This takes the two-phase from two-phase relative permeability and generates three-phase relative permeability. So it says if you inject WAG, then you have three-phase now. If you have this two-phase KRO, KRG, that would be your three-phase equivalent. What we've done is we've taken a piece of rock in our lab and we scanned this to make sure there is no heterogeneity, any geology issue. We know this very well. This is a bucket of sand, very homogeneous. And then we've injected water and gas into this core to generate two-phase relative permeability. Exactly the same thing that a practicing reservoir engineer would do. So we've generated two-phase relative permeability. We then perform a WAG injection. We've in fact performed a series of these WAG injections. And then we have measured the production. If you use this oil and this reservoir rock and did WAG injection, how much oil and gas and water will you produce? What would be delta P across this rock? We've measured these in our lab. And then using that data, we use the existing three-phase models in simulator to compare prediction in terms of oil recovery, additional oil recovery from this WAG experiment. Prediction from reservoir simulator, different models that you have, and comparing that with what we've actually seen in our lab experimentally, right? We've used different models. And here's what we've seen. So this is the additional oil recovery by WAG injection in this system. This is how much oil you've recovered. This is how much water and gas you've injected. And this blue curve shows that how much oil you've recovered. Because you inject one cycle of gas followed by one cycle of water, you could see that you have some humps in these curves because not oil and gas would equally produce the same amount of oil. Sometimes gas produce more, sometimes water produce more. So in any way, this is the additional oil recovery for that WAG experiment. And then we have looked at prediction of models. Here's one model, Baker 2. So you see that there's a big discrepancy between what Baker produced and what we've actually measured for the same condition. This is another one, SWI method. This is another one. This is Baker 1, Stone 1. This is Larson. And this is another model, Stone exponent. So you could see that none of them actually agree with the experiment, right? But perhaps more importantly, they don't even agree with each other. Now, if you are predicting performance of WAG in a reservoir here, you don't have this. Which one of these do you go for? Which one of these is correct? Probably none. By look at it, you probably think, but none of them is correct. But which one do you choose? Which model? We've looked at then the error involved in using each one of these models in comparison to the actual measure that we have the answer because we've done this test. And then we've compared that. And you get different sort of error values. In some cases, you could see that the error could be as high as 250%, right? 250% error between the difference between the amount of additional oil that the model produced for you or predicted for you and the actual value that you obtain in the field. So how much additional oil recovery are you hoping to get by applying WAG? How much additional oil recovery you are hoping to get? 10%? 12% if you're lucky? Pessimistic scenarios, 3-4%, right? So if you're after that, if you have 250% error in your model, no management, you can ask David, would approve something like this. No management, right? And that is why out of that 90 million barrel of oil that we produce, only 250,000 come from EOR. No oil company is interested in producing more oil. Let's be clear. Companies, oil company like any other business, they are in the business of making more money, looking after the shareholder, right? So if there is uncertainty in applying EOR, people won't do it. They go and do something else. They move to other areas, right? Leave that for later. And this is the challenge of EOR. The size of prize is absolutely enormous. The challenge is these things. We don't have good models. Not physical, not simulator. There are problems with both of them. Our experiments that we do are mostly wrong. Our simulators are mostly wrong. The tools that we use for EOR prediction, they've not been designed for this. Numerical simulator is good for history matching, and that's how it's been developed and used. But now that you want to predict EOR, these are not fit for purpose. New ideas needed here. And this is the sort of things that you need to think about. We've developed our own simulators to address some of these problems. I'm not going to go through these, but we've addressed some of this. Paulo, I have more, but I think I've overstepped my time. So I'll just stop here. But if you have any question, please let me know. But I repeat again that it's really an exciting time. I tried my best to convince my daughter to do a PE degree. But she said, after what you did to our life, I'm not going to do PE at all. She chose to do medicine. But I do honestly recommend to you to consider moving up from where you are. And there are a lot of opportunities. The time is now right. I wish I was like yourself starting today, because looking back, I think I wasted probably 2 decades of my life by being born 2 decades early. Right. Any question or any?
If you have any questions, please raise your hand and introduce yourself for the first time. Mehran, Brazilian candidates are very reactive, and you presented several techniques for enhancing oil recovery. In your opinion, what should be the best technique for such a reactive rock such as?
So this is a system similar to the Brazilian carbonates. This is the core. It's probably Sean's hands here. Is that right, Sean, in this photograph? So this is where we've injected fluid through this rock. And it's a carbonate rock. See that hole in here? We call this wormhole. When we CT scan this hole is actually like this. So going deep in the rock and having sort of side branches in there. How do you model this? This could be a good thing and could also be a bad thing. It could be a good thing because when you have this around your well bore, you increase your injectivity. You can inject much faster per well, which is a major problem. Each well here is probably costing $500 million to drill. So your wells are extremely limited, but also causes problem. How would this affect the properties? How would this affect your well bore stability, etc.? So I think, first of all, for EOR, there is no silver bullet. There is no one size fit all. You need to work on each system separately. And this is one of the difficulties for EOR. And this is one of the reasons why you need to have experimental facility to be able to run experiment under reservoir condition, to be able to see these things. I don't think there is a single solution that anybody can mention. But certainly CO2 injection, because you have CO2. And often the choice of what you do in your reservoir, the choice of what you inject in your reservoir is dictated by what do you have access to. The reason why every reservoir in the North Sea is underwater flooding is because you have plenty of water there, right? Why that is not done in Canada? Where do you get water from in Canada? Why it's not done in Oman? There is no water to inject in reservoir. In here, probably CO2 injection is a good idea because you have plenty of CO2 as part of the associated gas that you produce. But then we need to be careful about this geochemistry. And then you have a multi-physics and chemistry problem to solve. You have the multi-phase flow that we just saw, which, by the way, didn't include any of these complexities of geochemistry. Now, when you add this geochemistry to that multi-phase flow, and then change of physical properties of the rock or petrophysical properties of the rock, then you have a very difficult problem to solve. There is no single solution. These carbonate rocks are extremely complicated. They have a lot of micropores. Micropores changes behavior of these rocks. We've tested them against other rocks, and the behavior is completely different because of the internal geometry of these rocks. But we have been able to alleviate some of these problems. You could choose the composition of the water that you inject in the reservoir so that you have a more compatible water, and we've actually avoided this type of wormhole generation in the same carbonate rock by the choice of the type of fluid that we inject.
Right, thank you very much.
I have a question. Just for curiosity, how well do these models perform in history matching? Because we know that history matching is one thing, but predictions.
How well the models perform in history?
Models, when the history match, they are really good, and then
For a certain amount of time, they're good. So if I said that in a reservoir, the oil production rate has been moving this way for 10 years, right? This is the trend for the past 10 years. If I ask you, how would this go for the next 2 years? What do? Just extrapolate this, right? And say this is probably where you will be. They are fairly good for history matching, because those relative permittivity curves that I said are difficult to obtain, you could obtain them based on history matching to see what curve would match this history best. And then you get those history matched relative permittivity, and then use that relative permeability to predict sometime in future. But as people in the stock market would tell you, is that past performance is no guarantee for future performance. So there's no guarantee there. But what you do, you refine it again. And that's why I say they're good for history matching, but not good for prediction. And for EOR, you need to be able to predict, because there is no history. In EOR, there is no history. Some people mistakenly believe that generally when you do EOR, is a sort of late stage life of a reservoir. You've been producing from your reservoir for 20, 30 years. And people, and in this 20, 30 years, you have plenty of wells drilled, you have plenty of rock, sample of fluid, testing, data, etc. And then you may think, well, this is really good for EOR, because I now know reservoir much better than I knew 20, 30 years ago when the production started. That is true. But what is missing here is that now your oil saturation is less than before. And this oil is much more difficult to produce. So although you have better data for reservoir, but really that second half which is left in the reservoir is much more difficult and requires much better understanding to produce compared to that first half that has already been produced.
Any other question? So, thank you very much, Mehran.
Thanks a lot.